Dear students, in this session, we will discuss the short-run production function. That is, we consider change in output resulting from a change in one of the inputs, keeping all the other inputs constant. Keeping all the other inputs constant. As stated in the earlier class, we use the production function Q as a function of K and L. We use the production function Q as a function of K and L. And this production function shows the maximum amount of output Q that can be used, that can be produced using alternative combinations of capital and labor. Production function shows maximum amount of output that can be produced by using different combinations of capital and labor. Now we define marginal product. Marginal product. Marginal product is defined as change in output resulting from a 1 unit change in one variable input, holding all other inputs constant. And it is known as marginal product of variable input. So marginal product is change in output resulting from a 1 unit change in one of the variable inputs, keeping constant all the other inputs. Now we define marginal product of capital as equal to limit of delta K is equal to 0, delta Q by delta K. Delta Q by delta K is equal to dou Q by dou K is equal to Fk. So MBK is the limit of delta Q by delta K, that is dou Q by dou K. We use the notation Fk. Similarly, MBL is the limit of delta L equal to 0, delta Q by delta L is equal to dou Q by dou L, and we denote it as FL. If capital is the variable input, this is MBK. If labor is the variable input, this is MBL, Fk and FL. And the mathematical definition of marginal product utilizes the concept of partial derivatives, something which is familiar to you from basic calculus classes. Now we might expect that marginal product of an input depends on how much of that input is actually used. Marginal product of an input, say capital or labor, depends on how much of that input is actually used. For example, labor cannot be added indefinitely to a fixed amount of land and fertilizers without eventually exhibiting some deterioration of productivity. So if you apply more and more labor to a fixed amount of land, keeping constant fertilizers, there will be an eventual deterioration of the productivity of labor. Mathematically, the assumption of diminishing marginal product is an assumption about how the second order partial derivatives behave in the limit. Mathematically, assumption of diminishing marginal product is an assumption about how the second order partial derivatives of the function behave in the limit. That is, dou MBL by dou L is equal to dou square Q by dou MBL by dou K is equal to dou square Q by dou MBL by dou K is equal to dou square F or dou square Q by dou K square is equal to FKK less than 0. Similarly, dou MPL by dou L is equal to dou square Q by dou L square is equal to FLL less than 0. That is, the second derivative is negative. So mathematically, diminishing marginal product of capital is denoted as FKK less than 0, of labor as FLL less than 0. Now the assumption of diminishing marginal productivity was originally introduced by 19th century economist Malthus. Malthus worried that rapid increase in population eventually results in lower labor productivity. He believed that rapid increase in population results in eventual decline in marginal productivity. But this position need not be true in modern times. Change in MBL, marginal product of labor, over time depends not only on how labor input is growing, but also on other inputs. What happens to MBL over time depends on how labor input is growing, how other inputs are also growing. Mathematically, we have to consider dou MBL by dou K is equal to FLK. That is change in marginal product resulting from a change in other inputs. Dou MBL by dou K, we denote it as FLK. And in most cases, this FLK is greater than 0. In most cases, this FLK is greater than 0. So, declining marginal productivity resulting from an increase in L or K is a foregone conclusion, not applicable in the real world. And as it is known to you, since the time of Malthus, there is a tremendous increase in the marginal product of labor due to technological progress and also due to an expansion in the capital input. So, we have to consider what happens to MBL when there is a change in other inputs, dou MBL by dou K, that is FLK, and in most cases it is greater than 0. Now, we consider a specific production function to explain these points. Now, this specific production function is Q is equal to explain the behavior of marginal product and also average product, which we will see. We use the cubic cost function 6L square minus 1 by 3 L raised to 3. As you can see, this is a short-run production function. And what is peculiar about this production function is only labor input is variable. All the other inputs, including capital and technology, are held constant. Now, what is MBL? MBL is dq by dl is equal to 12L minus L square. MBL is 12L minus L square. Now, this graph represents this protection function. This Q is equal to 6L square minus 1 by 3 L square is L cube is shown as TPL. The corresponding MBL is given by this curve MBL. And as we know, MBL is nothing but the slope of TPL. MBL is dq by dl, the slope of TPL. And as the graph shows, at the lower levels of labor usage, TPL increases at an increasing rate up to point S. TPL increases at an increasing rate. So, the slope of TPL, that is MBL, is increasing. The slope is increasing. Or we will say that total product of labor curve is convex. And what is peculiar about S is, this is the inflection point. Inflection point means the point where the curvature of the graph changes from convex to concave or from concave to convex. Here from convex to concave. So, at the point of inflection, the slope is maximum. And this can be easily derived like this. Dou MBL by dou L is equal to 12 minus 2L. And we equate it to 0, which will give us L as equal to 6. And if you take the second derivative, dou square MBL by dou L square, it is equal to minus 2 less than 0. Second order condition for maxima is satisfied. So, L is equal to 6 is the point where the slope is the maximum, or MBL is the maximum. Slope of total product or MBL is maximum. Now, to the right of S, as you can see, total product is still increasing, but at a decreasing rate. So, MBL is positive but declining. MBL is positive but declining. And in the maximum point, we will have slope of total product is maximum and MBL is 0. So, MBL is 12L minus L square. We equate it to 0. MBL is 0 means MBL is 0 means total product is maximum. 12L minus L square is equal to 0. This can be written as L into 12 minus L equal to 0. L into 12 minus L is equal to 0, and we have L is equal to 0 or L is equal to 12. So, when L is equal to 12, total product is maximum and the marginal product is 0. And finally, when total product is declining, marginal product is negative. A firm will not operate where MBL is negative. So, a firm will operate only when MBL is greater than or equal to 0. So, this is the conventional shape of TPL. and the slope of TPL, MBL like this. Now in common usage, the term labor productivity often means average productivity. So we define APL as APL is equal to Q by L is equal to F of KL by L. APL is average productivity and we define it as Q by L. And in general, average product is total product divided by any input. And as you can see, average product of labor initially increases, reaches a maximum, then decreases. This result can be derived like this. We know that APL is equal to Q by L is equal to 6 L square minus 1 by 3 L cube divided by L. Production function divided by L is equal to 6L minus 1 by 3 L square. Q by L is equal to 6L by 1 by 3 L square. And dou APL by dou L is equal to 6 minus 2 by 3 L. We equate it to 0 and you will get L as equal to 9. So average product is maximum when L is 9 units, and this is confirmed by dou square APL by dou L square is equal to minus 2 by 3 less than 0. Second order condition for maxima is also satisfied. So APL is the productivity of labor. Average product is maximum when the number of units of labor used is 9. And as you can see here, the productivity of labor as shown by APL changes as additional workers are employed. This is because all the other factors are held constant. Now as you can see, initially at first, when the usage of labor is small, then as more and more laborers are employed, APL increases up to 9 units of labor, because initially other factors are abundant in supply, but labor is only small. Naturally, as more laborers are employed, productivity of labor increases. But a point is reached when labor is no longer limited compared to other inputs. So it results in APL declining after some time. In this figure, APL decline when the labor usage is 9 units. And also note that APL is always non-negative as long as total product is non-negative. As long as total product is non-negative, APL is also non-negative. Remember that point. MBL can be negative, but APL is always non-negative because APL is TPL divided by quantity. And graphically, we can determine APL from TPL by drawing a line through the origin. If you draw a line through the origin to any point on the TPL, then APL is the slope of that line. For example, when L is equal to 3, Q is equal to say 45. So that APL is equal to 45 by 3 is equal to 15. So if you want to derive APL graphically, you draw a straight line from the origin to any point and take the slope. So at point H, the slope of this straight line is maximum. That means this is the point where APL is maximum. So this is consistent with the 9 units of labor. So this is the short-run production function represented by an equation from which MBL and APL are derived. And in this example, we treat labor as the variable input, capital, technology, etc. as fixed inputs.